In this last section on two-dimensional dynamical systems, I want to emphasize some of the new features of two-dimensional systems that do not exist in one dimension. The first point is that there are new types of trajectories, namely limit cycles. Limit cycles arise when a steadily driven system somehow goes into a motion which involves self-sustained oscillations. Some examples of this might be oscillating chemical reactions, or a much more dramatic example is the Tacoma Narrows Bridge collapse. Here, a newly opened bridge over the Tacoma Narrows suspension bridge was subjected to very high winds, and it turns out that the winds were just such that it excited torsional oscillations in the roadbed, leading to the eventual collapse of the bridge itself just very soon after it was opened. These sorts of self-sustained oscillations have very important practical effects. Another important feature of two dimensions is that one can infer the existence of limit cycles by topology, namely by something known as the Poincare-Bendixson theorem. And so the idea behind this theorem is extremely simple. Let's suppose that we have a region of space. So here's some region in two-dimensional state space. And suppose, for example, that the flow everywhere is inward, everywhere along the boundary of this region. So the conditions we need is that we need inward flow on the boundary. Then, if there is no fixed point in R, then the Poincare-Bendixson theorem guarantees that there must be a limit cycle somewhere inside this region. So the idea here is that if flow is inward, it has to somehow converge somewhere. But if there's no fixed point, then the only possibility is a limit cycle. Now, one last point I want to make about new features in two dimensions is that there's also new types of bifurcations. Namely, we studied in one dimension simple bifurcations, but there's a new type that exists in two dimensions known as the Hopf bifurcation. And we'll see this in action momentarily.